Good morning everyone. Today, I'll be talking about one of the most widely used algorithms in machine learning, the decision tree. This algorithm is a foundation for many predictive models and plays a key role in both data science and business analytics. My goal today is to help you understand what a decision tree is, how it works, where it's used, and what its advantages and limitations are. Let's begin with the basic concept. A decision tree is a supervised machine learning algorithm. That means it learns patterns from labeled data that already has known outcomes, and uses that knowledge to make predictions or classifications on new data. The name, decision tree, comes from the fact that the model literally looks like a tree. It starts with one main question or condition, which we call the root node, and then branches out into possible answers, or decision paths, that lead to outcomes at the leaf nodes. Think of it as a structured way to map out decisions. Each internal node asks a question, each branch represents an answer, and each leaf node gives us a final decision or prediction. Now, let's look at how decision trees are applied in real life. They're incredibly versatile. For example, in banking, a decision tree might be used to determine whether a loan should be approved. The algorithm can consider inputs like a customer's credit score, income, and repayment history. By following the branches, say, is the credit score above 700, or, is the annual income greater than $50,000, the model arrives at a decision like, approve, or reject. In healthcare, decision trees can help predict diseases. For instance, a model might use patient data such as glucose level, body mass index, and blood pressure to predict whether a patient is likely to have diabetes. In education, they can predict student outcomes, such as whether a student is likely to pass or fail a course, using factors like attendance, study time, and grades. In customer analytics, they're widely used for churn prediction, identifying which customers are likely to leave a service, and for fraud detection, where the model flags suspicious transactions based on patterns in past data. So, in short, decision trees are everywhere because they mimic human decision-making, just much faster and at scale. Now, to make this more concrete, let's walk through a simple example. Imagine we want to predict whether a customer will buy a product. We have three variables: age, income, and whether they've made previous purchases. The tree starts at the root node, where we might ask, is the person's income greater than $50,000? If the answer is no, we might immediately predict, no purchase. But if yes, we move to the next internal node. Is the person's age above 30? If not, again, no purchase. But if yes, we check the final factor. Has the person made previous purchases? If yes, the prediction is purchase. If not, no purchase. That's how a decision tree breaks a problem into smaller, simple decisions, each one moving us closer to an outcome. Now, let's briefly touch on how we actually build a decision tree using Python. In this case, we're using the Titanic dataset, which contains information about passengers, their class, gender, age, fare, and whether they survived. We start by loading the dataset with pandas, select the relevant features, and handle missing values. For example, by replacing missing ages with the average age. Next, we encode categorical variables like gender into numerical form, because machine learning models work with numbers, not text. Then, we use scikit-learn's decision tree classifier to build the model. After fitting the model to the data, we can evaluate how well it predicts survival. In this example, the model achieved a score of 0.97, which means it was able to correctly classify 97% of the data, a strong performance. Though we must remember that such high accuracy can also be a sign of overfitting. Now that we've seen how it works, let's look at why decision trees are so popular. First, they're easy to understand and interpret. The tree structure itself is visual and intuitive. You can literally trace the decision path from top to bottom. Second, they require little data preparation. You don't need to normalize or scale data as you do for many other algorithms. Third, they can handle both numerical and categorical data, making them extremely flexible. Fourth, decision trees can help with feature selection. By showing which variables were most important during the splits, you can see what drives predictions the most. They can also handle missing values, work well for both classification and regression tasks, and capture nonlinear relationships that might be missed by simpler models. However, decision trees aren't perfect, and it's important to understand their disadvantages as well. The biggest drawback is overfitting. A tree can become too complex, learning every small detail and noise from the training data, which makes it perform poorly on new data. They're also unstable, meaning small changes in the data can lead to very different tree structures. Another issue is that trees are often biased toward features with many levels. For example, categorical variables with many unique values might dominate splits, even if they're not truly important. On their own, single decision trees are often less accurate than ensemble methods like random forests or gradient-boosted trees, which combine multiple trees for stronger performance. Finally, building trees with continuous data can be computationally expensive, since the model must check many possible split points to find the optimal one.